Hello and welcome to part 2 of the Hohmann equation. Now, one neat thing about the Hohmann equation is that not only does it calculate for the speed that you're leaving Earth at, because in this case I used Earth and Mars, but it also calculates for the velocity that you'll be at when you reach Mars's orbit. And despite popular belief, your velocity isn't the same, because as you get farther away from the sun's gravity wants to pull you back in, so therefore you're decelerating. So, to calculate for this, you use v Mars equals v Earth times the radius of Earth divided by the radius of Mars, which gives me a resultant of using my numbers of 21.915 kilometers per second at Mars's orbit. So, actually to achieve a low Martian orbit, I needed an additional 3.53 kilometers per second. So I did a vector addition like shown in my first video. If you haven't seen it, you should watch it. It's tons of fun. But anyway, I did a basic vector addition taking the velocity Mars is traveling in its orbit and the velocity needed to remain in a stable Martian low orbit, and I was able to come up with that I need to be going at approximately 24.33 kilometers per second, which, yeah. And now, even though I know how fast I'm going to be going, and I need to know the distance I'm traveling in order to determine how long it's going to take, because that's rather important. So the Ramanujan approximation is a very accurate approximation developed by a brilliant Indian self-taught mathematician who died in the 1920s. And many of his formulas have actually been proven to be fairly accurate. Like, this is a very accurate representation on how to calculate the distance of an ellipse. And since there's no set formula, I chose this one because it was rather simplistic for me to understand too. So basically what it's taking is the semi-major axis, A, and the semi-minor axis, B, and use the formula, and P is the perimeter of the ellipse. So if I wanted to draw a diagram, this would be the ellipse, and this would be the center of the ellipse, this would be the semi-minor axis, and this would be the semi-major axis. And the semi-major axis is going to be longer than the semi-minor axis. So, oh, and this one is A, this one's B. Forgot to say that. So basically, I used that to be able to calculate for how many kilometers it would be for the mission and how long it would take. And I discovered that it would take approximately 245 days to go from Earth to Mars using my calculations for my mission, which I will explain at a different time. However, that's how long I discovered it would take, and by using the distance and the time, the distance and the speed, I was able to calculate for how long it would take. Thanks, and have a wonderful day.